All right. So, so we already decided the work done for that, right? The work done is just mgh, and so it's technically it's 300 times 24 kilograms times 10 meters per second squared, that's 5 meters, and that's what we got, 360,000 joules. That's the work that has to be done, right? And Mary's forklift delivers a power of 600 watts. So how do I calculate the amount of time?
The power divided. Or the watts divided.
So power is work per time, right? And we want to get to time, so what do we have to do? How do I solve that for time? Are we all stuck on this? I'm going to start by teaching algebra. Yeah, I multiply both sides by time and then divide both sides by power. Right? And so this is power, time times power is equal to work over time times time. Right? Multiply both sides by time, the times cancel, and then I divide both sides by power. Time times power is equal to work, time is equal to work over power, and that's equal to 360,000 joules or 600 watts. Right. And so that cancels two of those zeros. I get 600 seconds, maybe. Let's see. I do, because I do 36 by 6. 10 minutes. Is that right? Lucy Sky, or is it just my handwriting that you're boggling at?
Yeah, what's the last one? Did you say 10?
Yes.
Yeah, okay.
Yeah, it's just terrible handwriting. So that was 58, 59. If a forklift is 25%, how much energy does it consume doing this job? So this is the same problem we asked to answer a few minutes ago about Bob, right? not all of the energy that goes that your car consumes goes into doing whatever work your car is doing or whatever. It can deliver 600 watts of mechanical work, but it has to burn more than that in gasoline, or what do they call that? No, that's not what I was thinking of. Propane or just whatever they run those little electricity, I guess, maybe those little forklifts and stuff off of. Probably electrical. So how do I calculate this?
You take the joules and divide it by 14 times.
Yeah, so again, the efficiency is the work you do divided by the energy you have to consume to do that work, right? And so they're asking us how much energy it consumes. And so the energy is the work divided by the efficiency. The equation, the algebra that got us to here is the same algebra that got us to solve that problem, right? If A equals B over C, right? And C equals B over A. That's what we're doing in all of this. Algebra is important, right? And so that means the energy she consumes is the 360,000 watts, joules, sorry, divided by 0.25, which is just 4 times that, which is I think like 1.44 times 10 to the 6th, or 1,440,000 or something. So number 60 says, how much was it for? No, 10 cents. What was it? 10 cents per kilowatt hour. So if energy costs 10 cents per kilowatt hour, what's it cost Mary to do the job? Who can tell me? Right. And what is that energy in kilowatt hours? This is in joules, right? So we have to do the same conversion we did a minute ago. I'll do it over here. All right. The energy is 1.44 times 10 to the 6th joules, but we want to convert that to kilowatt hours. So we're going to write it's a watt times seconds per joule. Right, and then we're going to multiply it by 1 kilowatt over 1,000 watts. And then we're going to multiply it by 1 hour over 3,600 seconds. Right, and the seconds cancel just like before, and the watts cancel, and the joules cancel, and I get kilowatt hours. And if you do this, it comes out to, I think it's 0.4, right? Because this is 3.6 times 10 to the 6th. And if I divide this by 4, I get 3.6 times 10 to the 5th. So it's divided by 10 and multiplied by 4. So you can do that math however you want to. The price you have to pay is just the rate times the energy you consume, right? And so that's just 10 cents per kilowatt hour times 0.4 kilowatt hours. Right. So Bob has to buy three Snickers bars, and Mary has to spend 4 cents.
Did you do number 9 from the work of energy?
Was that number 60?
Yeah.
Oh, great. So the same set, but number 9. Yeah, I think the right answer is not on that one. I think someone brought that up. Is that what you're asking? Who asked me that?
I don't know. One of my friends that's on.
Okay. Yeah, this one says, somebody came by and asked me about this one. I think the right answer is not there. A box of mass, but let's just talk about it. Box of mass, 8 kilograms, is dragged along the ground with a force of 50 newtons on a leash, which makes an angle of 37 degrees above the horizon, above horizontal. It's like this. 37 degrees. Yeah. The coefficient of kinetic friction is 0.8 if the box is pulled 5 meters horizontally. What is the work done by the friction force? So use K equals 0.8. The box is pulled 5 meters horizontally. Right. So what do I do? What's that? Yeah. So how do I calculate the normal force? Why do I need the normal force?
Because force due to friction is okay.
Yeah. So if I want to get the work done by friction, I need the force of friction times the distance times the cosine of the angle between them. Right. That's my work equation. So I'm going to have to plug into that somehow. As Nick correctly said, well, we need to get this. We need to get what this F is, right? It's F sub K. And so we went straight to the definition and said, well, the force of kinetic friction is mu sub K times the normal force. What's mu sub K? Yeah, we already got that from the problem. It's 0.8. And so now we're thinking, well, what's the normal force, right? That's this guy, right? So how do I get the normal force for this thing? Say again? I had a dinner the other night with like 50 people and everybody was talking and I couldn't hear anything. I'm almost deaf. So I'm like that old man now who just stares at people and doesn't say anything.
You don't hear them.
But I have to communicate with you guys. So I'm just going to keep saying what. I'm sorry. It's my fault.
The force times distance times cosine theta.
Well, yeah, that's the work, right? And I've lost track. I talked for too long. And we're trying to figure out what this guy is, right? Which way does this guy act? In the upward direction, right? So is it just the opposite of gravity? Could we just figure out what gravity is? Why not?
Just.
Because this guy has a little y component also. Right? There were probably some questions before we got to this one. Probably, I don't know, but probably.
Yeah.
And so usually when I'm doing these in learning catalytics, I'm walking us through a bunch of questions, right? And so we're just jumping into the middle of the swimming race, right? On lap 6. And so we've got to kind of backtrack a little bit if we're going to have a conversation about this. So I've got a normal force. What other forces do I have acting in the y direction?
Gravity.
So I've got the force of gravity. What's the equation for that? Equals what? Mg, right? What other forces do I have acting in the y direction?
The y component.
The y component of this guy, it's got an x component and a y component. And so f sub y is equal to f sine of 37 degrees. Right? Did they tell us what the f was?
50.
So this is 50 newtons. Right? And so I'm guessing 50 newtons times the sine of 37 is probably 30 newtons. Because I don't pick those numbers by accident, usually. Right? And so it's the sine of 37 is probably 0.6 or close to it. And so that's probably 30. Right? And so what does that say about the normal force? So what's the net force on this box without thinking about anything that I just said? The box is sliding horizontally across the ground. What's the net force in the y direction on the box? 0. It's not moving in the y direction. There's no acceleration in the y direction. So if I add up all the forces in the y direction, they have to add up to 0. I have 3 of them, right? I have this one, and this one, and this one. And what did we say the mass of the box was? 8 kilograms. So 8 kilograms times 10 meters per second squared. This guy is 80 newtons. Now, can somebody tell me what the normal force is? It's got to be 50, right? The normal force has to be 50. Why?
Why? The force in the y direction is 30 to make it equal.
What has to be equal?
The gravity and gravity.
These two guys have to add up to this guy, right? That's what has, if there's no net force in the y direction, all the team that's pulling up has to exactly equal all the team that's pulling down, right? I've only got one guy pulling down, he's 80. I just told you this guy is 30 up, so this guy has to be 50 up, right? With these problems with an extra angled force in there, that's what you get, right? You have to sort of figure out how that affects. Usually what it changes is the normal force. If I'm pulling up, notice this, if the rope wasn't there, right, what would the normal force be? 80, right? The normal force has to exactly balance the weight. But because this person is pulling up on it a little bit, it eases the load on the normal force, right? The normal force is how hard the table is pushing up on my laptop, right? If I lift up on my laptop a little bit, then the table doesn't have to push up as hard. It just needs to keep the computer from going through the table, right? And so it just has to accommodate whatever fraction of gravity I'm not accommodating. So 80, 30, 50. And so this is 0.8, I think it was, times 50 newtons, which is equal to 40 newtons. Right? How does that help me? The force, which is now 40 newtons, times the distance, which is what? 5 meters, times the cosine of the angle. What's the angle? So what's the direction of the of it's moving? What's the direction it's moving in the picture? To the right, yes? What's the direction of the friction force? What's the direction of the friction force? To the left, right? So what's the angle between them? 180. What's the cosine of 180? -1, right? The friction force is sucking the work out of the system, right? If the friction force wasn't there, this box would be accelerating and speeding up and stuff to the right, but friction is just pulling energy out of the system so that it can't do that, right? And so this is, so our work done here is F sub K times distance times cosine of the angle between them. That's 40 newtons times 5 meters times the cosine of 180 degrees. That's equal to 200 joules times -1, which is -200 joules. I suspect whoever asked me that calculated this and said, hey, that's not a choice. You're right, I'm just goofed over.
How would you use questions getting like the network done?
So. So. So the network done is what?
Net force times the distance.
So what's the net force? So what's the net force in the y direction? Does everybody agree with that? We already said that. It's not moving in the y direction. So now we have to figure out what the net force is in the x direction. Well, what forces are acting in the x direction? Okay, so let's talk about the friction force. Which way does friction go? To the left. What's its value? No, that's that negative. It's just 40 newtons. You can call it -40, but it's 40 newtons this way, right? So we're just going to put an arrow on it and say it's 40 newtons that way. If we have to add it to something that's pointing the other way, we'll put a negative sign for it, right? So what's going the other way? So what do we call that? We're going to give it a name first. You're right. F.
X.
Yeah, Fx, right? We did Fy. Let's call it Fx, right? That's this piece. And that's equal, what did you say? It was force times.
Force times cosine 37.
Right, it's this piece now, right? And so that's 50 newtons times the cosine of 37 degrees. I'm going to guess that's 40 newtons. You can tell me what the cosine of 37 is, but I'm going to guess it's 0.4. Point 8. Point 8, right? Who's checking my work? Am I just talking?
39.9.
For this, but you got probably
Yeah.
0.79 something here. Yeah, okay. And so now tell me again, what's my net force in the x direction? 0. What's my net force in the y direction? What's the net force on the box? What's the net work done? All the force of balance. Individual forces are doing work, right? What's the work being done by the x component of the pull force? You should be able to tell me that just by looking at what's on the board. Say again?
Would you ask?
What is the work done by this force? Yeah, it's the same force as this one numerically. It's just pointing in the direction it's moving. And so it's just the work done by this force. So I'll call it WFX. This is just equal to Fx times the distance times the cosine of the angle between them. And that's just 40 newtons times 5 meters times the cosine of what?
Oh, no.
Well, that would be,
All right. So it's like talk to each other. What is it?
cosine of force of X.
This, what angle is that we're talking about? It's the angle between what and what?
Okay, well, it's zero, going in the same direction.
Let me ask it this way. I'm not arguing with you. I'm not arguing with you. But if I say the work is equal to the force times the distance times the cosine of theta, that's the definition of work, right? That theta is between what and what? The force and the distance. We agree on that? So what's the direction of the force? This way, right? It's the x component of this guy. What's the direction of the distance? Also that way. It's the way the box moves. What's the angle between them? 0. Right? I mean, you should be able to work those out. I know you had it right now. I was just working through the whole thing. We were all talking about it, hearing different answers. So this is, I mean, it's important to try to take yourself back to the definitions. It's easy to get confused in a problem that's got a million angles in it. Right? Some are right angles, 90 degrees, some are 37 degrees, some are 180 degrees. What angle do I plug in there? Go all the way back and say, well, what force am I looking at? I'm looking at this force. What distance am I talking about? I'm talking about this distance. The angle between the force and the distance are in the same direction. The box is moving in the direction the x component of that force is pulling it. And that's the piece we're talking about. And so it's 200 joules. It's 200 Newton meters, and Newton meters a joule. It's 200 joules, right?
Okay, this is gonna sound like a stupid question. So this box can't be moving, right? If there's no net work being done and the forces cancel each other out, the box isn't moving, right?
Well, it moved
Well,
five.
it
It
how
moved
did
5 meters.
Yeah, how did it move if all the forces there cancel each other out?
So what's the net force on that stapler? If it's moving with a constant velocity,
It doesn't have an acceleration. Okay, fair enough.
so once it's moving, it can keep moving with a 0 net force acting on it, a 0 net force acting on it, right? I mean, there's a little subtlety to that, but as long as it's already moving, somebody had to pull it to get it started, right? But once it's started, it's just going along at a constant velocity. It's got no acceleration. So the friction force is exactly balanced by the push force. And then the net work that's done on it is 0. And so really what's happening is I'm doing work on this thing, right? The force from my hand is pushing on this thing, clearly exerting a force, and I'm doing work. So where's the energy from my work going? Yeah, so where is that manifesting itself physically? Where is it showing up? If you were a, I don't know, an engineer or a chemist or something, you were going to find that energy. Where is it? Yeah, it's heating the table up, right? You could tell it if I just did this a whole bunch, eventually the table would get warm, right? But I'm just doing a little bit of it. I marked up the table. I'm just doing this, right? 66 on momentum or energy, working energy. Okay.
Almost the same one.
All right, on the one we just did. Working energy, so I don't need that one. Momentum. And you said which one? Number 12, Tristan, let's see. Toy car of mass 2 kilograms is traveling to the right at 3 meters per second, is acting on by force of 2.5 newtons in the negative direction for 4 seconds. What is the change in momentum of the car? Is that what we're on? Okay. So I didn't remember any of that. A toy car mass 2 kilograms traveling to the right at 3 meters per second. I have this 3 kilograms or is it 2 kilograms?
2 kilograms,
Good God.
have 3 years.
3.
Force is 2.5 newtons
It's 2.5 newtons.
for 4 seconds.
And so did I say it right?
Yeah, 2.5 newtons for 4 seconds. But I
So go ahead.
think it's in the negative x direction.
Oh, it's in the negative x direction. You're right. So I'm going to say it this way, right? So the velocity is that way. F equals 2.5 newtons, but it's that way. Right. And the time is equal to 4 seconds. And what's the question?
What is the change in momentum?
Right. And so, so what's some of the vocabulary for this problem? There's change in momentum. So the change in momentum is equal to P final minus P initial. I'm looking for some language about this force and this time. If I remember any of those terms.
You mean the impulse?
Yeah. Now, what's the definition of the impulse?
Impulse is, force times change of time.
Yeah. So if you remember Newton's second law, F equals ma, we wrote that as, you could rewrite that as mass times the change in velocity over the change in time, because that's the definition of acceleration, right? And so then they took this piece of it, they said, well, okay, so that means the force is equal to mass times the change in velocity over the change in time. That's equal to, that means that the force times the change in time is equal to mass times the change in velocity if I multiply both sides by delta t. And then we call this thing the impulse. And the reason it's useful is it just comes up a lot. In sports, you hit a ball, you exert a force times a time, and you change the momentum of the ball. Or a car hits a barrier, and there's a force times a time, and it changes the momentum of the car. This is equal to, you just said, mass times V final minus V initial, because that's what delta V is, right? And so that's MV final minus MV initial if I algebraically distribute the M, and that's P final minus P initial, right? Which is what I had here, and that's just delta P, right? And so I can say the force times the change in time is equal to the change in momentum. And to me, this is sort of the cause and the effect, right? My car struck a curb at about 20 miles an hour. And there were a lot of effects, but my momentum went to 0. Jumped up in the air. And so what do we do with this? So this is I don't remember who said it. P final minus P initial. And the question was, what is the final? What is the change in momentum of the car, right? So who can tell me what the change in momentum of the car is without using a calculator? Sorry, this is momentum number 12 of the learning catalytics. For those of you watching at home. So maybe I don't have the volume on this thing. Other people are trying to ask me questions. Oh, okay. You've been helping me out, I guess, huh? You've been reading the chat. Thank you. I'll get to 7 next. Great. Okay. I was going to do. Well, anyway, we'll get to them. So who can tell me what the change in momentum is for the toy car? Why? Where'd you get that from?
It's just the first time.
Yeah, I mean, that's all it's saying is what's the force and what's the time? And the only thing you have to be a little careful about is just what Nick said. It's technically it's -10, right? Because what's the momentum of the car initially? Say again?
Is it 6?
Yeah, why? How'd you get that?
Mass times.
Yeah, here's the mass, here's the initial velocity. The car's minding its own business, rolling across the little kid's floor at 3 meters per second. Its mass is 2 kilograms, right? And so P initial is equal to mv initial, which is 2 kilograms times 3 meters per second, which is 6 kilogram meters per second. Right. Now, if it's gonna have a change in momentum by a force pointing this way, since I'm calling this positive, I can't also call the force positive, right? And so I have to say the impulse is minus 2.5 newtons times 4 seconds, which is minus 10 Newton seconds or minus 10 kilogram meters per second. Those are the same thing, right? A Newton is a kilogram meter per second squared, and so a Newton second is equal to a kilogram meter per second. And so the change momentum is minus 10 kilogram meters per second, or Newton seconds, whichever you prefer. And then the next question, 12, was that it for that one?
Well, is the answer not on that one?
Yeah, is that why someone asked me that? I have another one where the answer isn't right. It doesn't surprise me. Yeah, all right, so it's -12. It's -10. After all that, it should be, instead of +10, it should be -10. Yeah, that's it. All right. All right, and then somebody said what? Number 7 on that one, just while we're there. Ball, I should just check these first. Ball ASMS 3 kilograms traveling north. Ball ASMS 6 meters traveling west. All right, so how do I do this one?
Add vectors.
Yes. So this is north and this is east, right? And so this one, P1 is equal to 3 kilograms times 6 meters per second. And this one is P2. It's traveling west. It's 6 kilograms and 2 meters per second. So how would you figure out what the angle is? The total momentum.
Is it 22? Oh, are you on number 7?
I think so. What is the direction of the total momentum? In degrees from due east. Ball A has a mass of 3 kilograms traveling north at 6 meters per second. So it's doing 18 kilograms per second. Ball B has a mass of 6 kilogram and it's traveling to the west at 2 meters per second. So it's got a momentum of 12 Newton seconds. What is the direction of the total momentum of the system? What am I doing when I ask for the total momentum of the system?
Can we do this diagram here?
Yeah, I have to add these two, right? These two vectors. And so I've got one that goes this way and one that goes this way. So I can either take this one and put it at the tip of that one like that, and put my P2 that way and say, this is my P total. Right? Or I can take this one and put it at the tip of that one. Doesn't matter which order I add it to. Right? In either case, I get P tote squared is equal to the square root of P1 squared plus P2 squared, right? And what they're asking me for is that angle, right? That's what this question is asking me, right? What's the angle from due east of the total momentum? And so this one is, I can do that by instead calculating this angle and subtracting it from 180, right? So how do I calculate this angle? Tan theta is opposite over adjacent.
So 18.
Yeah, and so theta is equal to tan inverse of 18 Newton seconds over 12 Newton seconds, which is equal to what? 56 degrees. And so then this angle, which I'll call phi or something like that, which is what I'm after, is 180 degrees minus theta, which is 124. Is that a choice? Have we finally gotten to one where I had the choice right? All right. So let's see that. And we can calculate the magnitude too, right? It's the square root of 18 squared, which is 324 plus 12 squared is 144. 468, maybe 22 would be the magnitude. Was that another question? Yeah, question 6. All right. What was your question?
It was 66 on energy.
We'll go back to work and energy. We'll go back to 66.
It's 65, sorry.
65. We'll have a lot of questions tonight. Our 0.5 kilogram tool is now traveling 8 meters per second. The car is brought to a stop in 0.1 meters by constant force. What's the magnitude of that force? Yeah, that doesn't look right. Is that what you're going to ask me?
No, I really want 66, but also 65 too.
Yeah, so. Oh, this is a work question. Let me just see. Let's just look at that. Right. So this is a work problem. So this is number 66. Which one am I doing? 65?
Which the car is 65.
Yeah, okay. So number 65. So this is a toy car. So a toy car of mass 0.5 kilograms and speed of 8 meters per second is brought to a stop in 0.1 meters. Is that what it was? By a constant force. What is the magnitude of the force? And so how do I do this one? So work equals what? But now I need another formula for work. What's another formula for work? Yeah, there's something called the work energy theorem, right? Which says the work done is equal to the change in kinetic energy plus the change in potential energy. If the car is traveling horizontally, what's the change in potential energy? Yeah, because its height isn't changing. I mean, unless there's a spring involved or something, but that's not in this problem. Right, it's MGH doesn't change if its height isn't changing. So no, I just did. The work done is the change in kinetic energy, right? And that's the force times the distance times the cosine of theta, right? So if this is my car, and its velocity is 8 meters per second. What's the direction of the force going to be? It's brought to a stop in 0.1 meters. It's got to be this way, right? It's going that way. If I push it that way, it keeps going. Right? And so there's got to be a force this way. And it's brought to a stop in d equals 0.10 meters. Right? And so how do I figure out what the force is? Well, can we figure out what the change in kinetic energy is? So the work done on the cart has to equal the change in kinetic energy. I have to take all this, I have to push on it in such a way that all this kinetic energy goes away. Right? So what's this final kinetic energy? Right? So this is KE final minus KE initial, which is 0 minus KE initial, right? Because this final kinetic energy is 0. What's this initial kinetic energy? What's the formula for it? So what do I put in for M? And what's its V? So 8 squared is 64, right? Times 0.5 is 32. Divided by 2 is 16. Is that right? That's how much work I have to do. So if I'm going to stop it at 0.1 meters, what does my force have to be? Yep. Right. My work, which is the force time. So the work is from this formula, it says the work done has to be the change in kinetic energy, right? And start out with some kinetic energy, I'm pushing it in such a way that all that goes away. And then it goes away because I pushed it on it with a force over a certain distance with a certain angle between those two things, right? And I know the angle is, what's the angle? Yeah, the distance is which way? The car goes which, yeah, it goes this way while it's coming to a stop, right? And the force is which way? That way, right? I have to push on it that way while it's going this way to bring it to a stop. When I catch a ball, that's what I have to do. Push on it that way while it's going this way to make it stop. And so the cosine, what's the cosine of 180? So minus the force times 0.1 meters equals minus 116, is equal to minus 16 joules. Right, and so the minus signs cancel, I get the force is equal to 16 joules over 0.1 meters, which is 160 newtons. Is that even a choice on that one? Okay. What was the next one?
66.
So 66. There's another typo in there, isn't there? So a net force of 10 newtons acts on a box, which moves 2 meters in the direction of that force. If the box has a mass of 0.1 kilograms and starts off maybe at 10 meters per second, what's the final velocity in meters per second? So this is, did they give us a mass of the box? I got the memory of goldfish. 0.1 kilograms, the force is 10 newtons. This is 2 meters. So this is number 10 over the work and energy. No, sorry, number 66 off of work and energy. And it says a net force of 10 newtons acts on a box, which moves 2 meters in the direction of the force. 2 meters in the direction of the force. If the box has a mass of 0.1 kilograms, what is the final velocity of the box? Oh, it starts off at 10 meters per second. What's the final velocity of the box? And so how do I get this?
Calculate the work.
So what's the work?
So the work would be then 10 newtons over 2 meters.
So it's force times distance times cosine of theta, right? And so in this case, it's 10 newtons times what? Times 2 meters times what?
Cosine of 0.
because the box is moving that way and it's being pushed that way. So the angle between those two is 0. And so this is 20 Newton meters or 20 joules, whichever you prefer. How does that help me?
That helps you, then you just stick that number in, and then equal to changing.
Right, the work done is equal to the change in kinetic energy, which is KE final minus KE initial. Right, and that says that the final kinetic energy is the work done plus the initial kinetic energy. How's that going to help us find the velocity? This question is about the velocity. What part?
It's 1/2 mv squared.
Yeah, so if I'm looking for the final velocity, it's sufficient for me to calculate the kinetic energy. And in a work problem, that's usually what I'm doing. Even if I'm being asked for a velocity, if I'm doing a work problem, I'm probably going to calculate a kinetic energy and then unwind that somehow from the formula. Kinetic energy is 1/2 mv squared, right? And so I would say this is equal to, well, first let's say we already determined what the work does, right? The work was, right? The work was 20 joules. What's the initial kinetic energy?
1/2 of 1 10 squared.
Right, this was V initial squared. This is the mass. This is 1/2, right? 1/2 times the initial mass times the initial squared. And so that's 10 squared is 100 times 0.1 is 10 divided by 2 is 5 joules, right? It's 5 joules. And so now I can say the final kinetic energy, final, is equal to the work plus KE initial, which is 20 joules plus 5 joules, which is 25 joules. In other words, the thing had 5 joules to start with, and I shoved it, did a bunch of work on it, and upped its energy to 25 joules. And now I want to know how fast it's going. Right, and so I can just say, well, look, 1/2 mv final squared is equal to 25 joules, right? And so V final squared is equal to 2 times 25 joules over the mass, or V final is the square root of 2 times 25 joules divided by 0.1 kilograms, which is square root of 500 joules per kilogram. Right, because 2 times 25 is 50, divided by 0.1 is 500, and a joule is and then I have joules per kilogram. A joule is a kilogram meter squared over second squared, and so I'm going to divide out the kilograms. And when I take I'll have meter squared over second squared, and when I take the square root, I get about 22 meters per second. Or something like that. Is that a choice? I like 22.4.
Someone said 21.
Um, $21. Bicycle wheel spinning at 30 radians per second. Accelerates at 5 radians per second squared. And its radius is 0.35 meters. How far has it traveled after 5 seconds? what does the 30 radians per second represent?
Or
Which,
velocity.
more specifically, what angular velocity? You were on it.
Velocity.
When?
That would be.
When does the wheel, say again?
That's as far as I can get.
No, no, it's not. When does the wheel have that angular velocity?
Yeah, 6 seconds.
No, when does it, so tell me what's happening in the problem.
Spinning.
And then what does it do? It's, how fast is it spinning? And what happens? It accelerates. So does it keep spinning at the same rate? So what would you call that 30 radians per second? The initial, we have a name for that, right? What variable do we give that?
Yeah, maybe not.
Ah, omega naught. We have to plug these things into formulas, right? And so the omega naught is 30 radians per second. And then you said it's doing what?
Just wanting to know how far it travels in 5 seconds.
But before we get to that, what other piece of information did they give us?
Accelerating.
And what's that variable? What kind of acceleration are we talking about?
Acceleration.
So what's the variable?
So, like alpha.
Yeah.
Alpha is 5.
All right. So, and then later on it says, well, if it's got a radius of 0.35 meters, so R equals 0.35 meters, right? In 5 seconds. What's the 5 seconds? So, and so what do they mean by how far? What are they looking for? So this is a distance, which what letters do we, what kind of a distance? Vertical? What kind of distance? Probably horizontal. What variable do we use for that? X maybe, or delta X? So how are we going to go from angular stuff to translational stuff? Yeah, perhaps, right? And so first we've got to figure out like something about this and then connect it to something like this, right? And so there are a few ways to do this problem. So does anybody have a suggestion on that?
Find the average of the. We take the omega naught plus omega divided by 2.
So omega average is equal to omega plus omega naught divided by 2. All right, so we know what omega naught is. What's omega? Is there a formula for omega? Omega equals
Yeah, would it be 55?
probably, well, give me the formula first. You're right, probably.
Omega naught plus alpha times 20.
Right? And so it's final angular velocity. So my omega naught is 30 radians per second. Plus what? 5 radians per second squared times 5 seconds, which is what, Nick? So how does that help me?
Multiply it by the radius, and that gives you time velocity.
And I, same thing, I can get the initial velocity, right? And so I can say, if I wanted to here, I could say, look, V naught is equal to omega naught times r, which is 30 radians per second times 0.35 meters, which is like 10.5 meters per second, where I just dropped out the radians, right? What's my final velocity? So it's omega times r, which is 55 radians per second times 0.35 meters, which is, I'm going to say, that looks pretty good to me. 19 point something. So how do I get from there to the distance traveled?
Kinematics equation.
Yeah.
Yeah, you should get the average velocity.
Why do I want to do that?
So that way you could multiply it by the time. And then you can use the equation x equals x initial plus velocity, that velocity times time.
Right.
That.
Yes. No. Great. You did great. You did great. I was writing while you were saying it. It's great. And so I could use this equation. And so first I have to say V average is equal to what?
Is equal to the initial plus the final divided by 2.
Which is 10.5 meters per second plus 19.25 meters per second divided by 2, right? Which is, was that 30, about 15? Is that a choice? I think that's probably enough. Still got to put a few things together for tomorrow. I'll try to put this up. I've failed so many times now. I'm not making any promises.
The last one wouldn't open.
I don't think any of them have opened yet. Thanks, everybody.